Lecture we talk about the emerging number memory, and we talk about two array architectures. One is 1T1R, the other one is this cross-point array. And in the cross-point array, we have some problems with the sneak pass, and we discussed why we need the selector. So the other problem besides the sneak pass is the interconnect. So here we are going to discuss the interconnect wire resistance problem in the cross-point array. So here, if you look at the cross-point array, and here we have this 1S, 1R structure, one selector, one resistor. So we have those wires to form those bit line and word lines. So the problem is that the wire will carry some resistance. Although the wire may be made of the metal, you may have the copper as a metal wire. But even with copper, so the wire has some finite resistivity. And then if you think about the geometry of this very nanoscale wire, actually the resistance is not negligible. So here we plot the junction resistance Rj, which is defined as the wire resistance from cell to cell in this cross-point array, from cell to cell. So let's say one segment of the wire. And the resistance of this wire actually will increase with the scaling of the feature size f. And it's quite dramatically increasing as we decrease the resistance below 20 nanometer node. The reason is that the resistivity of the copper will increase at the very nano scale, like 10 nanometer or so. The reason is that the resistivity is coming from the scattering of the electrons when the electrons travel in the metal wire. So it will be bounced off from the green boundary or from the surface. Right? When the electron hits the surface, it will be bounced back. So that those kind of scattering will introduce the resistivity. So as you scale the size of the wire, then the surface to the volume ratio will increase. So that means the electrons will see more surfaces as you scale down. So then the resistivity will go up. And then as a result, the junction wire resistance will go up. So this is a problem for the cross-point memory array because of this wire resistance. So here you see the typical value for the resistance. So if your technology node, let's say f of this wire, the width of this wire is larger than 20 nanometer, then the junction wire may be like a few ohm. So this is kind of small. But when you scale the technology down below 20 nanometer, then this will exponentially increase. I think in your homework you will calculate some of those numbers for the wire resistance. So what you need to do is to look at the ITRS table we provided in the homework to find the resistivity as a function of the technology load. And then you need to calculate the resistance per segment. For example, here you may have one segment, right? So then you need to calculate what is the resistance, and you know this is R equals to resistivity times L divided by the area of this guy. So L for one segment in the cross-point array, you know, is 2F from cell to cell. And this width is F. And here the height of the wire is defined as this aspect ratio. Aspect ratio is the height divided by the width, and it's typically around 2 if you look at the ITS table. So that means this is the height is about like 2f. So you got those information, and then you will calculate the resistance per segment, and then depending on how many cells along that wire, you will get the total wire resistance for that VLAN or for that bitLAN. Okay, so this is how you calculate the resistance. But what would the resistance do for you in the memory array operation? So the problem is that it will shrink your read or write margin, because some of the voltage will drop along the wires. For example, here we consider the write operation. For this kind of margin analysis, so we should always consider the worst case. So what would be the worst case for the write operation? So if you think about the V/2 write scheme, you apply some write voltage to the row and you ground the column. So this write voltage needs to be delivered to the selected cell. And the worst case is that the cell is to the farthest from the, let's say, the write driver. So that is the farthest in this corner. And then this, if you simplify this array, then you will have the wire resistance for the whole row, and then you have your memory cell, and then you have another R wire. So this is essentially a voltage divider, right? So this write voltage, only a portion of that will drop on the memory cell. So we define this as a wave excess. That is the actual voltage dropped on the memory cell. So this is defined as the write margin, okay? And you need to consider the data pattern as well. What is the data pattern to make this worst case? So, you know, the voltage drop along the wire depends on the cell status, and because of those sneak paths, so when the cells are in the on state, it will make the situation worse, because the IR drop essentially is the voltage drop across the wire is due to the current multiplied by the voltage, by the resistance. So it's called IR drop. So if you have more current flowing through the wire, then you will have a larger IR drop. So when the other cells are in the on state, that means lower resistance. So you will have larger current. So then this IR drop will be more serious. So this is how you analyze the write operation. And for the read operation, it's a little bit more tricky. So the read operation, you also need to consider the worst case. First, where is the location of the cell? Still, the cell to this corner, farthest from the voltage supply or the ground will be the worst case. And then we need to consider the delta I, which is the current difference when this cell is in the on state or off state. You will read out two currents, and then you need to sense the margin between this on state and off state. So that will give you the read margin. So the read margin analysis is a little bit more tricky, and you may have to rely on the SPICE simulation to do that. Okay, so in principle, you can always build this kind of network into the SPICE simulator, and then you can play with the values of this wire resistance and memory cell resistance, and then you can get the write margin and the read margin. So this is the netlist you have to build in the SPICE. But if you do that, then you can run the simulations like this. So here, for example, you can get the write margin, which is the ratio of the voltage excess dropped on the cell over the VDD, which is the write voltage you apply from the edge of the array. So this ratio, and then you can vary the, for example, the width of your wire, like your technology load F. So basically, when you vary this width of the wire, you are varying the wire resistance, right? Remember the smaller width, larger wire resistance. And also another parameter you can design is the on-state resistance of your memory cell. And you can see here, when the memory cell resistance, on-state resistance is small, like 1 kilo ohm, then most of the voltage actually drop on the wire. So only like 10% of the voltage here can drop on the memory cell. That means when you apply like 2 volts to program your device, the farthest cell can only say like 0.2 volts, which cannot write the cell. So this is a write failure. This is not good, because this R is so low compared to the wire resistance. So don't ignore the wire resistance, because even though when you calculate this number, for example, you do that in your homework, each segment may only give you 1 ohm, but you are considering a large array, in this case 1 megabit array, that means 1000 by 1000 cell. You have 1000 cell along the word line or along the bit line. Each segment give you 1 ohm, 1000 cell will give you 1 kilo ohm. That 1 kilo ohm is comparable with this memory cell on-state resistance 1 kilo ohm. That's why you have this very bad write margin. So you have to boost your on-state resistance of your memory cell, like 10 kilo ohm, 100 kilo ohm. I think if you want to design large array, 100 kilo ohm is necessary. However, for most of the emerging technologies, 100K is not there. So typically it's in the tens of kilo ohm. So that will limit the array size. So similarly here, if we keep the on-state like 100 kilo ohm, and then we can vary the width, and then we can get the maximum array size to satisfy certain write margin. And for example, at 20 nanometer, you can get maybe 128 by 128 array working. So this is like maybe 256 by 256. If you consider the write margin. So any questions here? So essentially this will limit your array size. And by adding the selector will help. Okay. So you can reduce the sneak path. So you reduce the current flowing along that wire. So you reduce the IR drop. And also you can improve the write margin. So here are some also SPICE simulation results, considering the nonlinearity of the selector. So as we discussed before, the nonlinearity of the selector is defined as what here. So if you have some exponential IV, so here the ratio is nonlinearity ratio is defined as the voltage as the V and V over 2, and this is the ratio N. The current ratio between V and V over 2 for the selector. So you can see that the write margin. This is again the write margin. And for different array size, like 1000 by 1000 array size, you have to make the nonlinear ratio like 1000x. So here 1000 to make the write margin still larger than 80% for this very large like 1000 by 1000 array. Otherwise, your write margin will degrade as you increase the array size. So you can always do this kind of simulation by space to look at what is your design margin. Okay, so here is a quick summary for the challenges of the cross-point memory array design. As we discussed, sneak path is a problem. It reduces the read or write margin. And this nonlinearity in IV by the selector will be helpful to inhibit the sneak path. And wire resistance causes the voltage drop, or this IR drop, along the interconnect, which reduces the read margin and write margin. So to maintain the read margin and write margin, we need a selector, and also the memory cell resistance by itself needs to be high. So this is basically take-home message for the cross-point memory array design. But when you increase memory cell resistance, you may need to be careful because it decreases the read current and increase the RC delay. So the read latency may be slower. Okay, so those are the design considerations for the cross-point memory array. And in the next, we will briefly discuss the 3D exponent. So you may have heard of this before. Intel and Micron announced the 3D exponent memory technology back in 2015. And here are some of the introductions from the Micron's website at that time. So basically it's a cross-point memory array and it's 2-layer. So here this middle LAN is a shared bit LAN. So you have the 2-layer. So 1 layer here, 1 layer here. So each layer is a cross-point array. But the middle layer is a shared bit LAN. You have 2 VLANs, the top tier and the bottom tier, and in the middle you have the shared bit LAN. And this memory cell has this selector with it. So it's 1S, 1R structure. And this is basic information for the 3D exponent memory array. And when this was announced back in 2015, at that time Intel and Micron didn't disclose anything. They didn't say anything what's inside the 3D exponent. So people guess what is the material? Is R1 or is phase change? So what selector used there? And a lot of questions at that time. So you can read this list. I will not read this list. So Intel and Micron didn't say anything. They just put some, let's say, high-level performance number like the read bandwidth, write bandwidth, and the capacity of the total chip. They don't disclose any detailed information like the technology and the detailed material or even the technology load. So then, I think 1 year later, the company, TechInsight, did some reverse engineering of this chip because you can buy it from the market. And then they did some reverse engineering and then showed the report to the Flash Memory Summit, which is a major conference in the area of the non-volatile memory. And this is a report of that reverse engineering. So we can read some of the facts here. And the capacity of this chip, I think the first generation, that's 16 gigabyte. And if you look at the chip area, it's like this 60 millimeter by 12 millimeter. So in total, it's around like 200 millimeter square. And you have this 16 gigabyte capacity. So you can convert that to the density. Let's say the gigabit per millimeter square. So you get this number. And also, I think there are some other information you are interested in. For example, here, the word line bit line pitch is about 40 nanometer. And that means half of the pitch is the wire width, which is 20 nanometer. That is roughly your F. So this is the basic information from the 3D exponent. And then they did further materials categorization of this one. And by the TEM image, the transmission electron microscopy, as a cross-sectional view, you will see this kind of cross-sectional view for the chip. So the corresponding layer, those two layers, corresponding array, is on the top. I think it's between metal 4 and metal 5 here. This is like metal 4 and metal 5. It's not at the bottom. So underneath that, there are some contact wire for the transistors, or even here are some transistors. So those may be for the peripheral circuits. And some of the transistors may be hidden underneath the corresponding memory array. But the memory array itself is at metal 4 and metal 5 here. So here are the transistors. So the material characterization shows that the memory cell is a phase change memory, and with this kind of composition. So it's based on the GST material. And then this is a zoom-in view of that two-layer corresponding array from the side cross-sectional view. So this is a shared bit line in the middle, and then this is the top cell and bottom cell. And within each cell, you have the 1S, 1R. There are two devices in series. So here is 1S, 1R. And the memory cell is phase change memory based on this composition. And interestingly, for the selector, it's also based on the GST material with the ethnic in there. So it's so-called the OTS selector. So this is the basic information from the materials point of view. So this is chalcogenide based, essentially.
It's monolithic, right?
Yeah, yes. This feature says 20 nanometer, you cannot do any TSV. This is 20 nanometer.
So do they just happen to be on top of each other?
So you grow the material in sequence and then you etch. So they will self-align to be stacked on each other. Any other questions? Okay, so then here are some high-level performance benchmark using this 3D exponent memory versus DRAM in terms of the memory density. So here, I think the first few groups are different DRAM memory density. So from different vendor, from Samsung, from SK Hynix, from Micron, in around 20 nanometer technology node. So basically, those are the density in terms of the gigabit per millimeter square. So it's like 0.1, and this 3D exponent is like 0.6 gigabit per millimeter square. So it's much denser than the DRAM, as expected. But if you compare with the 3D NAND, then this is not there. So 3D NAND, as we discussed in the previous lectures, it reach like this 3 or 4, even 5 gigabit per millimeter square, depending on how many layers you use. But this exponent is like 0.6, so it's less density than the 3D NAND.
So exponent is only built on one, or there's 2 layers of exponent in the entire chip?
Yes.
They don't do multiple?
In the first generation, yes, only 2 layers. And I think we discussed before, this 3D exponent, 3D stacking is a simple stacking. It's not vertical channel kind of design. So that means you have to fabricate the first layer using one lithography, and then fabricate the second layer using another lithography. So it's not like the 3D NAND. So it's worse than the 3D NAND. Okay. From the density point of view, you see that it's between the DRAM and the 3D NAND. So later, Intel basically package this 3D exponent chip into the SSD, and with the PCIe kind of I/O interface, and it has 2 capacity. One is 16 gigabytes, the other one is 32 gigabytes. So the application is this high-end SSD. So essentially, it's the storage class memory between the DRAM and the regular SSD. So this is the so-called Octane memory. You can buy it from the market. And I think the initial generation, the first generation, cost like $300 per SSD for this 16 gigabyte or 32 gigabyte. It's more expensive than the regular SSD for the same capacity. And recently, I added 2 more slides last week because I checked some recent progress in this field. I don't think those slides are in the original uploads because I just added this last week. So I read some news that Intel is going to stack more. Previously only 2 layer. Now they are going to have 4 layers in the 3D exponent. So I think this maybe will be there maybe next year.
Why Flash can stack so many layers while VRAM is only a few layers?
Because it's a simply stack, right? So you, from the cost point of view, you don't gain too much, right? So this is due to the fabrication challenges. And actually later, maybe next lecture when we talk about the ARM devices, we can do similar 3D NAND kind of integration, and you can reduce the cost, but the fabrication challenge is there. So this simply stacking like this will be easy from the manufacturing point of view. But in principle, you can do the 3D NAND kind of integration. I will talk about that. That is in one of my chapter of my PhD thesis. I work on that 3D integration. for the R1 of exchange for this vertical channel, similar like the 3D NAND in the production, right? So my thesis is already like how many years? 7 years, 8 years ago. So, we'll discuss that next. Okay, so and another news is that Micron, okay, introduced this X100 SSD, and very recently, I think a few weeks ago. And I think the feature of this SSD is the speed or the bandwidth is super high, like 9 GB per second, which is like 10 times better than Intel's Optane SSD. So there are some news about the Micron and Intel. I don't want to go to the details. I don't understand the business there. So, but the news was Intel and Micron basically couldn't reach agreement on the roadmap of the 3D X-point array. So they initially co-developed the technology together in the IM Flash, the foundry there. But earlier this year, they decided no longer work with each other, so they want to sell their own product with different names, like Optane or X100. So then they stop the collaborations, and they want to specialize the process by their own roadmap. So that's the situation right now. Okay, so any questions?